Welcome to AI Frontiers, where we explore breakthrough research in computer science and artificial intelligence. Today we're examining a remarkable collection of discoveries from September 24, 2025, a single day that produced transformative advances spanning self-aware AI agents to quantum-inspired learning systems. These aren't just incremental improvements. They represent fundamental shifts in how we think about machine intelligence, collaboration, and the intricate relationship between human and artificial minds. Picture this scenario. You're working late on a complex project when suddenly your AI assistant freezes mid-sentence, begins repeating the same unhelpful suggestion over and over, and then crashes entirely, taking your work with it. Frustrating, right? But what if that same AI could recognize it was struggling and proactively say, "Hey, I think I'm getting confused here. Let me hand this over to someone who can help you better." That level of self-awareness in artificial intelligence isn't science fiction anymore. It's happening right now in cutting-edge research labs worldwide. What makes today's episode particularly exciting is how these 21 research papers connect to solve some of AI's most persistent challenges. We're exploring how researchers are creating AI systems that know their own limitations, how smaller models are outperforming giants through clever orchestration, and how artificial agents are learning to work together like a well-coordinated symphony orchestra. These fundamental shifts in machine intelligence collaboration and the delicate dance between human and artificial minds suggest that September 24, 2025 might be remembered as a turning point in AI development. To understand the significance of these breakthroughs, we need to appreciate the landscape they emerge from. Computer science artificial intelligence research, known as cs.AI in academic circles, is like a vast ecosystem where theoretical foundations meet practical applications. Think of it as a bustling metropolis where mathematicians, cognitive scientists, engineers, and philosophers all work together, each contributing their unique perspectives to the grand challenge of creating truly intelligent machines. This field has evolved dramatically from early rule-based systems that followed rigid logical structures to today's adaptive systems. It's the difference between a player piano that mechanically reproduces music and a jazz musician who can improvise, respond to the audience, and create something entirely new in the moment. The first major theme emerging from this research is metacognitive awareness. Essentially, AI systems that can think about their own thinking. Xu and colleagues pioneered self-monitoring AI agents that represent a profound shift from reactive systems toward proactive ones that can monitor their own performance and predict when they're likely to fail. Imagine an AI system as a skilled craftsperson who not only knows how to build furniture, but also recognizes when a particular piece of wood is too warped to work with and knows when to ask for help. This level of self-awareness prevents catastrophic failures and maintains user trust by ensuring smooth handoffs to human operators when needed. The second theme revolves around distributed intelligence and multi-agent collaboration. Rather than relying on single, monolithic AI systems, researchers are creating federations of specialized agents that work together like members of an expert team. Picture a hospital where specialists in different fields consult with each other on complex cases. That's the model these researchers are applying to AI systems. The Federation of Agents framework demonstrates how multiple AI systems can dynamically coordinate their efforts, achieving remarkable efficiency gains, in some cases 13 times better performance than single-model approaches. This finding challenges the prevailing assumption that bigger is always better in AI, suggesting that smaller, well-orchestrated models can outperform much larger ones. Privacy and security form another crucial theme, becoming increasingly critical as AI systems handle sensitive information. The Conclave framework demonstrates how AI systems can maintain both privacy and utility when processing confidential documents using sophisticated anonymization techniques that prevent cross-session entity inference attacks while preserving the semantic coherence necessary for accurate responses. This breakthrough proves that it's possible to have powerful cloud-based AI with confidentiality guarantees, opening new possibilities for deploying AI in healthcare, finance, legal services, and other domains where confidentiality is paramount. Now, let's examine the 5 key breakthrough discoveries that emerged from this research. First, the SAMULE framework demonstrates that AI agents can dramatically improve their performance by learning from failures across multiple levels of granularity, micro-level learning from individual mistakes, meso-level pattern recognition, and macro-level insight transfer. Second, researchers discovered mathematical equivalence between biological swarm behavior and reinforcement learning algorithms, finding that pheromone-mediated aggregation in C. elegans functions identically to distributed reward mechanisms. Third, privacy-preserving AI research proved that sophisticated anonymization can maintain both security and utility. Fourth, multi-agent orchestration achieves sublinear complexity scaling through hierarchical capability matching. Finally, quantum-inspired reinforcement learning substantially improves reasoning coherence in large language models by incorporating quantum mechanical principles. For our paper of the day, I want to focus on the work by Xu and colleagues on agentic metacognition because it represents such a fundamental shift in how we think about AI system reliability and human-AI collaboration. The paper, titled Agentic Metacognition, Designing a Self-Aware Low-Code Agent, addresses one of the most pressing challenges in contemporary AI deployment: the unpredictable nature of autonomous agents and their tendency to fail in ways that are opaque to users. The motivation stems from a frustrating reality that anyone who's worked with AI systems will recognize. Current AI agents often become trapped in unproductive loops or encounter unrecoverable failures without any mechanism for recognizing or communicating these problems to users. What makes this research particularly compelling is how it draws inspiration from human psychology, specifically the concept of metacognition, our ability to think about our own thinking processes. The architecture consists of two distinct layers: the primary agent that executes tasks within a low-code environment, and the metacognitive agent that continuously monitors the primary agent's behavior patterns. The monitoring system tracks various indicators predictive of impending failure: excessive response latency, repetitive action patterns, degradation in output quality, and deviation from expected behavioral patterns. When the metacognitive agent detects patterns indicating probable failure, it initiates a proactive handoff to human operators, with comprehensive context about the agent's attempted approach and specific failure indicators. This introduces 30 to 50% computational overhead, but substantially increases overall task success rates. The revolutionary implications extend far beyond low-code environments. The metacognitive monitoring approach could be applied to any AI system where reliability and user trust are important considerations. In healthcare applications, an AI diagnostic system could recognize when it's encountering a case outside its expertise and proactively involve human physicians. In autonomous vehicles, the system could identify situations where human intervention is needed before critical failures occur. Perhaps most importantly, this research suggests a new paradigm for human-AI collaboration, where handoffs are not viewed as failures, but as sophisticated capabilities that enhance overall system performance. The researchers also discovered that metacognitive capabilities could be transferred across different types of tasks and domains, suggesting that self-awareness in AI systems might be a general capability. Looking toward the future, these research directions paint a picture of AI systems that are fundamentally different from what we have today. Think of it like the evolution from rigid industrial-age assembly lines to flexible, adaptive manufacturing systems that can reconfigure themselves based on changing demands and conditions. The convergence of self-aware agents, distributed intelligence, and human-AI collaboration suggests we're moving toward what we might call symbiotic AI, systems designed from the ground up to work alongside humans rather than replace them. These systems won't just be tools that we use, they'll be collaborative partners that can adapt to our working styles, recognize their own limitations, and contribute their unique capabilities to shared goals. The efficiency breakthroughs suggest that sophisticated AI capabilities will become more democratically accessible, while privacy-preserving techniques point toward AI systems that can be both powerful and trustworthy. As we conclude today's exploration of these remarkable research developments, it's clear that September 24, 2025, represents more than just another day of scientific progress. The discoveries we've discussed collectively point toward a fundamental transformation in how we think about artificial intelligence. These aren't just incremental improvements to existing systems. They're paradigm shifts that challenge our basic assumptions about what AI can and should be. The movement toward metacognitive awareness suggests AI systems that are more reliable and trustworthy. The breakthroughs in distributed intelligence point toward collaborative systems that can tackle problems too complex for any single agent. The efficiency discoveries democratize access to sophisticated AI capabilities, while privacy innovations ensure that power doesn't come at the cost of user trust. We're not just building smarter machines. We're creating intelligent partners that can work alongside us to solve complex challenges. This research synthesis was created using advanced AI systems, including GPT and Claude Sonnet models for content analysis, with text-to-speech synthesis powered by Deepgram technology and image generation capabilities through OpenAI systems. Human expert review was conducted on all synthesized content to ensure accuracy and relevance. While every effort has been made to accurately represent the research findings, potential oversights may exist, and we encourage consulting the original archive preprint server references for complete technical details. The interdisciplinary nature of this research reflects the collaborative spirit driving modern AI development, where insights from multiple fields converge to create breakthrough innovations. Thank you for joining us on AI Frontiers as we explored these groundbreaking discoveries in artificial intelligence research. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive-preprint-server.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive-preprint-server.org.